Today this is the problem we are going to solve in Aster. So let's open first. So the problem is a bar which is 100 0.1 meter length, 0.01 meter width. So there is a 1 megapascal, 1 into e power 6 Newton is load is applying. Just go to geometry. First create the model. 0.01. So here 0.1, 0.01, 0.01. We can look here actually. So a bar. Now we need to create a groups. Create groups, face group. Just rotate using this. Okay. Add. This I'm going to fix it. So I'm naming as a fix. Here I'm going to apply load actually. So click add load, apply. So there is a volume group, just select steel, plain close. So now you can see here I'm going to fix. Here I'm going to apply a load. This complete body is a steel. So I have created a geometry. Now just go to mesh. We need to create a mesh now. So just right click, we are in the mesh. Just go to mesh, create mesh. So here assign set of hypothesis, 3D automatic excitalization. Instead of segments, just go to 1D, local length, give 0.05, plain close. Just create a mesh. So I have just 2 element across this. If you want to refine it, you just reduce the mesh size. Just edit mesh. Here you can edit it by changing this. Okay. So this mesh is enough for me. So now just create a group from geometry. Take these groups, plain close. So now I have did mesh also. So before going to the code Aster, I'm just saving this study. Now just go to code Aster now. So everything is done. Code Aster. So first I'm creating a stage first we need to import mesh or read mesh in code Aster or any solver. First we need to read the mesh, defining the material property, then assigning the material property to this geometry, defining the analysis and defining the model, then solving. So I'm going to read the mesh first. So it's reading the model from the Salom itself, MIDI format. Okay, just give OK. Then assign final element model. Finite element model. So I have only one geometry, so only one material, so that completely a 3D. So I'm going to apply everywhere to this. Okay, so this model is mechanic and this is a 3D model, so I'm applying this everywhere, a mechanic and 3D. Okay, just give OK. Then material, we need to define material first. How we can go, material is a steel which is Young's modulus is 210 gigapascal and Poisson ratio is 0.3. So here this is a linear isotropic model. Young's modulus is 210 e power 9. Giga means e power 9. Poisson ratio 0.3. Okay, just give OK. Density is not required. If you want to solve a self-fit problem or frequency analysis problem, that density is important. Here any two properties required, either density Young's modulus or Poisson ratio Young's modulus. Okay, now just assign a material to the mesh. This is a mesh we have. Just at least any one. Model everywhere, only one material we have, this material, so just choosing OK. Instead the material name, you can name it as a steel. The steel will be assigned edit, so you can see steel. So this is OK. Now function is not required, boundary conditions. So here we are going to fix it is, just go to this, assign a mechanical load, enforce degree of freedom, elemental group. We can apply as a nodal group also, elemental group. This is the fix. I'm going to fix it. What I'm going to do, I'm going to fix lesson and cast elements, completely fixing it. Okay. Then another one. This is rename it as a fix. Only condition again. Now I'm going to apply a force on the face. See, force on the face. Elemental group, load, next direction. I'm going to pull it. So here you can see 1 into 10 power 6 Newton. This is a force on the face. While applying to the solver, so it will be applied as a pressure only. So just go to here, power. So by seeing it, 1 to e power 6 divided by 2 more 0, we need to add it, e power 8. Now load also applied. Post processing, calculate. No, we need to specify the analysis before. So load we have applied, so we need to define the analysis. So linear static analysis. Mechastatic is the solver. So result material. So element property is not required here. Model is FE model. Loads. Fix. One more. Load 0. So these two loads. Solver I have specified now. Just go to post measuring, calc camp, result calculation. Need to calculate sigma. Directional stress we need to calculate in element as well as node. Directional stress, then criteria, von Mises stress we need to calculate, element and equivalent stresses. So nodal equivalent stresses, then force on the reaction nodal. So this thing we need to calculate, then we just go to OK. Now everything is done. We need to write the file, output file. So set output results. So I'm writing as a static underscore bar dot rmed. Rmed is the file format we are the Salamica is using it. Result, again edit. So we need to mesh result both. Here what things we need to write is displacement and sigma directional stress. Sigma in directional stress in node, equivalent stress in element, equivalent stress is node, then finally reaction force. Okay, so these are the output we need, so that's why I'm choosing it. Okay, so now everything is done. You can see geometry I have created in Salom, then mesh I did. Initially I'm importing the mesh into, reading the mesh in the code Aster, defining the model, defining the material property, then assigning the material property to the model, then applying the boundary conditions, then defining the solver, what analysis we need to do, then calculating stresses. So then output, saving the stresses for view the plots. Then we need to save the file. So I'm just saving this file. Okay, go to history view, current case. I have just 1 GB RAM actually, so you can set, if you have multi-core, everything you can set here, number of threads also, everything. So I have 1 GB RAM, that's why I'm specifying 1024. Just click this add, then auto refresh, just set it as a 5 second, then just run it. Now the result solver is done. You can see a green, yellow with tick mark, green with the tick mark. So just select this, post processing. This is x displacement, I mean this is magnitude, this is dx. We need to see the directional stress. Actually, just go here, sigma xx. Yeah, so the stress is around this is the color, you can see 1e�8. So load is 1e�6, load by area we are getting 1e�8 is a directional stress. So this is due to the constraint we are getting very high stress. So by the analytical equation will be applicable away from the boundary conditions. By seeing the stress value here, this is the stress actually. Instead just go to para. Open. Static bulb. Just apply. Displacement, yes. Now we can change this color also by clicking here. Yes, just click this. Yes, blue to red rainbow. Apply, close, and set this value as, instead of 256 just give us 20. Okay, just keep this here. This is the result. This is a displacement in direct direction. We need to see directional stress. We can compare the stress. Now you can check the result actually. Sigma x, see, in this you can see in sigma xx, in SIGMNOEU, the first one is sigma xx. So sigma xx is 1 e power 8. Okay. Now we can see the Van Mies stress. Just go to magnitude. This is a Van Mies stress. Sigma xx and Van Mies stress is almost here same. Leave this location because of this boundary condition. Okay, fixing that's right. Similarly, Tresca stress, then 3 principal stresses: principal stress 1, principal stress 2, 3. So next we can go for the deformation. Just right click, add filter, common, just warp by vector. Just click this, scale factor something, just give 10, just give apply. So just go to set the displacement, magnitude. We can animate this, create a new animation track by ramp with 10 frames. Okay, here you have this animation. Loop we can set, or just click this ramp. By animation, okay. Thank you all. Please subscribe my channel for more videos.